Hey, welcome back to my shop. Back when I bought my milling machine, the Optimum MB4 tabletop milling machine, I also bought this Vertex rebranded as Optimum rotary table. This is a made in Taiwan unit, and it's quite good. I posted a teardown video of this guy quite some time ago, and I will put a link down in the description to the teardown. And when we had taken this apart, most of the details in this rotary table were quite good and well made, but I wouldn't be who I am if I wouldn't go for a complete overkill rebuild on a piece of equipment that I have. So I thought about it, and we're going to take this rotary table apart. We're going to scrape all the mating surfaces. We're going to tighten up the plain bearing, the radial bearing in here, which is just sliding a bushing, a shaft riding in a cast iron bushing. We will tighten that up, and we will scrape the axial bearing surfaces of the rotary table and the rotary table itself. Yeah, that's the general plan, and some smaller things I want to do. I want to cut a keyway in here that mates up with the keys of my milling machine, or with the T-slots of my milling machine for alignment, and a few more little things. So let's go over to the milling machine, and I will show you what I mean with the key slot. Okay, first thing you might notice is that the holes in the base of the rotary table do not line up with the T-slots of my milling machine, and that's really annoying. You could use one of the holes with a stud and a strap clamp back here, but that's even more annoying. So what I did, I made these two clamps out of carbon steel. These are hardened and tempered to roughly 45 Rockwells, so they last. And those slide in. And clamp the rotary table down here on this flange against the table. And that works quite well. At least for my purposes, this is most of the times way stiff enough. If I need a more rigid setup, I can add a third hold down clamp on the rear side of the table, the rotary table that is. And I leave those clamps always set up with the screw, with the T-nut, and with the clamp itself. So when I use the rotary table, I just take out those two clamps, pack them in the slots, and I'm good to go. That makes for quite a fast transition to the rotary table. Same when I use the rotary table in a horizontal configuration like this. I have a T-nut, a hex screw, and a very heavy hardened washer. These are also turned from 45%, 0.45% carbon steel, and hardened and tempered. And these go in here and lock the table down. Same on the other side. Those also always stay together in a box. together with the rotary table. So while the alignment of the table in the horizontal position is not relevant, you could clamp it this way, or this way onto the table, and it wouldn't matter because the work is rotating 360 degrees around. It only changes your zero setting, but apart from that, it doesn't matter. It matters if you have the rotary table up in a vertical position and you want to do accurate work. The rotary table needs to be aligned square to the travel of the axis. And on my rotary table I have surface ground this lower edge here. So I can do a rough alignment with a machinist square or run an indicator along this edge for precision alignment. But that's still one step more to do before I can start working. What I want to do is I want to cut a key slot in here into the base of the rotary table. Where I can use a pair of precision keys for alignment. These are hardened and ground to very close tolerances. You can buy those readily available. They are ground very precisely and they fit into the keys of a machine. And you can use them for semi-accurate alignment of tooling. It helps if you have two of those keys quite far apart, but that's not possible in the case of the rotary table because the base is only that wide. But I still can slip in two of those and then I can push the rotary table up against the keys and it will align itself quite accurate. We have to do all the machining, all the real machining and material removal on the rotary table before I start to scrape anything on it, because any machining will cause distortion in the cast parts. Yeah, and to do the machining we'll take the rotary table apart so it's not so freaking heavy when I have to lift it around on the machine. Okay, while we're at disassembling, I'm also going to take off the worm gear from the table. So that's the rotary table, the spindle with the round spigot, which gives a radial alignment in the housing. And I'm just giving the spigot here a quick check with the micrometer, and it's out of round. Not very much. It's 45.01 here, 45.005 here, and 45.0 here, so it's about 1/100th of a millimeter out of round, and we will fix that too. While we have it apart, we will compare the diameter of the spigot here to the bore in the housing. So I already measured it up, and the spigot is 45.01. And the bore in the housing, I'm just taking a rough measurement with the 2-point internal mic, is 45.05. So we have 400ths of a millimeter clearance. Clearance or clarence? It's clearance. So I'm surprised that the difference between those two diameters is so big, while it does not affect the precision of the rotary table as much as I would expect. I could only measure a play in the spindle of about 100ths of a millimeter, and I blame this to the heavy oil I run in this rotary table. The oil film around the spigot in the bore seems to be stiff enough to keep it centered enough and in place. So the 400ths of a millimeter gap between those two parts, which is almost 2/1000ths of an inch, doesn't affect the work. But that said, I want to tighten this up. I think I'm going to machine this diameter down by 1 or 2 millimeters in diameter. I will machine a sleeve out of some steel. I'm not sure about the material combination yet, but I will Loctite the sleeve on and then machine and lap it to final diameter. And I will do something with the bore, but I'm not sure about lapping the bore in cast iron, because cast iron is quite soft and I don't want to embed any kind of abrasive in the bore. So I still have to do research about lapping cast iron. Okay, I got the rotary table back over on the milling machine, and I centered it over the two T-slots, and I will cut a keyway into the housing of the rotary table back here. And I already did the calculations where the slot has to be. It's 42.87 millimeters, so 43 to this side of the slot. And I will machine a matching key to my machine out of this piece of tool steel. I will harden it and then I will grind it to width. So it's a very close, very tight fit in the T-slots. And if I remember right, the slots on this machine are 14 millimeters. This is a 14 millimeter gauge block stack, and it's a rather loose fit. So we have T-slots, and the nominal dimension for the slot itself, A, is toleranced with H8 for alignment and clamping T-slots. H12, which is a far looser tolerance for T-slots that are only for clamping. Let's assume the slots on this machine are for clamping and alignment. So H8, that's 14 H8. Let's go into tolerances, ISO tolerancing. Let's see, large H8, nominal dimension 10 to 18. H8 is, let's write this down, it's 14 plus 27 plus 0. And this means that our slot can be, the numbers in the tolerance tables are in thousandths of a millimeter. So our slot can have a tolerance of 14.000 as the smallest dimension and 14.027 as its largest dimension. So we should not be able to get a 14.03 millimeter gauge block stack into those slots if they are to spec, which is questionable on a Chinese machine. I have a 14.03 millimeter stack of gauge blocks here, and I cannot slide it into the T-slots, so that's good. So that means that the slots are to spec. Let's try a 14.02 millimeter gauge block, and this is a nice fit if you don't drop the gauge block stack. So the 14.02 millimeter gauge block stack is a very nice sliding fit in the T-slot. That means that we're going to machine the key to 14.02 millimeters after we harden it, of course. Okay, that was a very quick excursus into tolerances and reference book and so on. So we'll just start by machining the T-slot into the base of this rotary table. I don't want to make this key slot in the rotary table too deep because I don't want to weaken the casting too much. Okay, to clamp the casting I bolted a box parallel to the table of the machine. It's aligned in the X direction already. And I take my casting, or the housing, and I will bolt it against the box parallel, just like this, with a long stud through there. Okay, got it bolted against the box parallel. Now I'm leveling out the top surface. Okay, let's check our alignment, and obviously the surface drops. Still dropping, and now it's rising, so that's looking good. We start at 22 over here, and when we traverse to the other end, we are still at 22, maybe half of a hundredth of a millimeter. I added a second clamp down here, so the setup is safe. With only one stud in the center, the work could rotate, and the second clamping strap clamp down here with the bolts through it, this can take up the torque that would rotate the part and mess up the job. So, okay, when I machine the key slot into the base of the rotary table, I want it to be square to the base, of course, otherwise it would be useless. So I broke out the 0.02 of a millimeter dial test indicator, and I'm rechecking my alignment. I already tweaked the setup slightly by loosening the bolts that hold the box parallel to the table, and I knocked it slightly into alignment. And when you watch the needle of this rather sensitive indicator, you will see that you see nothing. Just double check. Okay. Most of the needle jittering is surface roughness. But we are pretty much 0 dead knots on. And yeah, the indicator was in contact. See? So I think that's pretty good aligned for the job at hand. Okay, I'm using a 6mm 3-flute carbide end mill to cut the slot to a width of 14 plus a little bit. Okay, I got a 14.03mm gauge block stack here, and this should be a very nice tight fit in the slot. And it slides all the way to the bottom of the slot with a little bit of wiggling, so that's a rather tight fit. That's a rather tight fit that I like. I prefer to work the sides of the slot with a stone if the fit is too tight, but I don't think that that is necessary. I think I did everything that's possible in this setup. I ran the chamfer mill around the edge, I machined the slot for the key, and I tapped two M3 threads to hold the key in place. So let's tear down the setup and proceed on. Okay, stoning the back of the rotary table before we go to the surface plate. Using a diamond ground aluminum oxide stone, I surface ground the stone flat on one side using a diamond wheel on the surface grinder, and this works really well when stoning precision surfaces. I always cringe when I when I saw people using some random stone like this carborundum stone and going frantically around a machine table or something like that, and yeah, scratching it all up. So I never did it actually. I always used the palm of my hand to feel if there is somewhere a ding or something that needs to be stoned just in the area. But the precision ground stone, you can buy these, and Robin Ranzetti showed them in his video, and he wrote somewhere in the comments a little bit about them. The surface ground stone is not as aggressive cutting as a stone that's normally dressed, and behaves a little bit different. If it sits flat on a flat surface, it's really only sliding around. But as soon as there is a ding or something like that in the surface, the stone starts to act differently, and you will see or feel the cutting action of the stone on the raised area. And when you take a close look, you will see a highlighted area, a fresh exposed metal around the ding. That's where the raised up metal gets removed. Just imagine like this. You have a flat surface and it gets hit with a pointy object like a center punch. It will look like this in cross section. There will be raised material here and here and a deeper area. And we only want to cut away the raised area with the stone. We do not want to alter the surface in general. What you can also do before if you see the thing before, you can take a ball peen hammer and you can peen back some of the material before you stone it. That way you don't lose as much material and you can close up the thing more or less. So I use it wet. And of course, you do not use such a stone to hone your lathe tools, because first of all, it doesn't cut as well, and second, you don't want to mess up the precision ground surface. If I hold a straight edge up to this is dead flat in two directions. If I hold up a straight edge to the small stone here, this is chowdered up in every possible direction. I have my new to me Mitutoyo Hikator 2 set up on the surface plate. This is a 1/1000th of a millimeter indicator. These are built by Mar for Mitutoyo. Actually, it says exactly that on the back side. Made in Germany by Mar for Mitutoyo, which is quite neat. Didn't know that Mitutoyo did resell measuring equipment from Mar. I always thought they are competitors, but it seems that there is some kind of working together. So this guy is super nice. This type of indicator has only a very limited travel. It goes from -0.05 of a millimeter to +0.05. So it's 1/10 of a millimeter complete travel, and they don't have backlash. This type, a normal indicator has a backlash of a 1/100th of a millimeter indicator has a horrible amount of backlash. These don't. So you bring them onto the surface you want to measure, and you have a fine adjuster here, so you can zero them out. It has about ±0.05 of a millimeter adjustment, and the fine adjustment is one of the nicest I have ever used. Compared to the fine adjustment of an indicator stand, this is like butter. Using the fine adjustment on most indicator stands is like using a battle axe for brain surgery, something like that. But this, you can pinpoint your zero so nice without a problem. And I'm using the heavy Mitutoyo height gauge with the twin columns as an indicator stand for it, and that seems to be rigid enough to do that job. So I walked my way around and I have written out all the difference in height in thousandths of a millimeter. And as you can see, we start at 0. It drops slightly over here to -0.03 of a millimeter, then it goes back up, then we have a divot of 0.03 over here, and that goes up back to 0. So, and all those numbers are in 1/1000th of a millimeter. So what these numbers tell me is that the bottom surface and the sliding surface for the rotary tables, for the actual rotating part, is pretty good parallel. There were, as I said, this rotary table is out of the box really very nice piece. Only thing that annoys me slightly is the big play in the bore, but parallelism wise it's a nice piece. And while I will scrape it, I will scrape the underside and this slide and this bearing surface here. I will not change the geometry because that's okay. That's well within 5,000ths of a millimeter. That's 2/10,000ths of an inch, roughly. So I'm going to single point bore the central bearing diameter, and then I will go from there. I already checked it. It's slightly bell-mouthed to the bottom, which is also bad, but we'll sort it out. We'll take the wall hopper boring head or my other smaller boring head, and we will clean up this hole, make it round and cylindrical. That was quite a bit of talking. I clamped the rotary table casting flat onto the table, and I have already my small boring head that can pass through the bore in the spindle, and I'm centering on the original bore, or I already centered. As you can see, we start here with 0. I spin it around. We get also 0 plus parallax error, which you cannot see on video, or you see the error on video, but I can show look down straight on the dial, so there is no, this is 0, 90 degree to the back, and you can see that we have 0 back here too. Now spin it again 180 degrees to the front, and we get 0 in this position too. That's the bore centered. What I want to check too, because we're boring with the quill and the power feed, I want to check the tram against this surface, this bearing surface, which is within reasonable tolerances parallel to the bottom surface. We measured it before. It's less than 5,000ths of a millimeter out of parallel, so I can consider this surface right now as parallel. Oh, and I found something out. When I tighten these table locks down too hard, I can bend the table by 5,000ths of a millimeter. It makes a bow in the Y direction. It gets like this. If I cram too hard on these table locks. Same for the cross piece, the Y-axis. If I lock the axis too hard, it bends. That's the problem with direct acting locks, not the blade type lock you would have on a jig borer or on a jig grinder. So that's also a reason why you should not over tighten stuff on machines. Like table locks or quill locks or drawbars or everything. Nothing on a machine needs 100 Newton meters, except for ER collets. Those take ridiculous amounts of torque, but that's other topic. Adjustment screws and stuff like that do not need to be over tightened like crazy. Okay, I double checked everything 5 times, and now we're about to bore the central hole. I set the tool so it takes a very light cut, and that's all I need. I just want to clean up the bore and make it nice, round and straight. So let's go, 300 RPM, and we're feeding with 30 millimeters per minute. Okay, I will clear the tool slightly so I don't scratch the surface when I retract the quill. Okay, here you can see the surface finish we got, and this looks really good. I will take a close look if we clean up the whole surface, but looks promising. I took about 1/10 of a millimeter on per side, and that should have cleaned up everything. Okay, I wanted to show you the tool I used for boring, and this is just a high-speed steel Cobalt 8 blank, and it's ground like a turning tool, and I lapped the surfaces with a stone to a very, very good finish. And I also hand lapped a very small radius on the cutting edge. You can see this line of light here, that's the radius. The radius is down here in this, on this cutting edge. So with the radius I get this rather good surface finish. And also you can see that I don't bother with lapping the whole surface. It's just important to lap all the way up to the edge. The rake surface here does not need to be super high polished when you're working with steel or cast iron. If you're working with aluminum, a high polish on this surface can help with chip evacuation, but I don't use aluminum very much, so